This presentation will be about linear independence and spanning sets. For linear combination, it is defined to be the scalar multiplication of vectors with scalars and applying vector addition to each of these vectors to get any vector inside the vector space, given that all of these vectors are part of the vector space and all of the scalars are all real numbers. So as you can see in this diagram, we can see that we have different vectors of different lengths and magnitude and direction, and you can see that when you add them together, it forms this vector v, which is basically, again, a combination of all the other vectors that are added to them. Next, we have the null space, defined to be the subspace of all solutions of the homogeneous system A times x equals 0, also known as the solution space, with A being the coefficient matrix and 0 being the zero vector. Then we also have the spanning set, known to be a subspace of all vectors in V, which are a linear combination of the vectors in S, denoting that S spans V. And if span S is equal to the vector space, then S is a spanning set of V. So as you can see in this diagram, we can see that these are the vectors, and the spanning set, span S, is the set of vectors that you can create using these vectors inside the set. And if again, span S, or the vectors that you can make with these vectors inside the set, is equal to the vector space, then S is a spanning set of V, meaning you can create any vector inside the vector space V using the vectors in S. So for example, let's say in a 2D space, we have two vectors in our set. And when you combine them together, you can create a lot of vectors within the 2D space, or in the Cartesian plane. So let's say you want to get to this vector. And to get to this vector, you can add or multiply a scalar to this vector, and then add it to another vector multiplied by some magnitude in the scalar, which could get you to this vector. Additionally, you can also do this for another vector like here and add them like so. You can start with this one and then combine it with another vector like this one to get to this vector. So if you can create all the vectors in the 2D space in the case of this one, then it is considered to be a spanning set. This also extends to 3-dimensional spaces and other dimensions higher than 3. So in a 3D dimension, you can create any vector in the space given your 3 vectors. So for example, if you want to get to this vector, you can add this vector, then this vector, and then let's say another vector, which will get you to this vector in the 3D space. Now, how can something not be a spanning set? For the case of 2D spaces, if your set of vectors can only span a line, meaning the set that it spans given the set of vectors that you have are limited to only these vectors within this line, then it's said to be not a spanning set because you're not able to reach the other vectors outside this line. Similarly, for a 3D space, it's considered not to be a spanning set if and only if the spanning set only forms a plane. So we could make it look something like this, meaning all the vectors that you can span using these vectors that you have are only limited to this part of the plane. You cannot like extend over here or maybe over here, which means that it wouldn't be a spanning set because you're not able to reach other vectors using the vectors that you currently have in your set S. So now let's have some examples regarding spanning sets. So first, let's identify if this set is a spanning set. So first, we have our 3 vectors, and we can use the concept of a linear combination to be able to solve this problem. So first, let's create the linear combination for with this set of vectors. So let's have our scalar A multiplied to 1, 3, add it to another scalar B, and then add it to another scalar C with the vector 0, -2 equal to xy. Xy in particular is any vector in R2. So, with this, we can actually turn this into a system of linear equations, which would look something like this. And then 3a minus 3b minus 2c is equal to 1. We can also turn this into an augmented matrix of the form like so. So this is 1, 2, 0, 3, negative 2, and xy. And we will use this augmented matrix and convert it to its RREF form. So this RREF form will show us what kind of solution we will get and whether it determines whether this set is a spanning set or not. And when you get the RREF of this augmented matrix, you should get something like this. And this one would show us the following equation: A minus 4 over 9, C is equal to 2y plus 3x over 9. Similarly, we have B plus 2 over 9c equals 3x minus y over 9. So here we have an example of the vector of the set of vectors that we have and giving the resultant vector. So here in this example, we can our constants that we used for this example are a equals 1, b equals 1, and c equals 2. Which when you use these on the as a linear combination with these vectors, this gets you to the answer 3, -4. So what does then these equations tell us with regards to the set of vectors that we have? These showed some sort of relationship or equality between the result of the vector and the constants when you apply the linear combination to these set of vectors. So when you use these constants and substitute it for this equation and use the x and y values for this vector and in these right-hand side of the equation, we will get first 1 over 1 minus 4 over 9 times 2 equals 2 times -4 plus 3 times 3 over 9. Similarly, 1 plus 2 over 9 times 2 is equal to 3 times 3 minus -4 over 9. And if we simplify both sides of the equation, we actually get 1 over 9 on both sides of the equation. Similarly, for this second equation, we actually get 13 over 9 on both sides of the equation. So the fact that they're equal with the constant, and there is some sort of relationship with the constants and the resulting vector, that means there will always be a solution for every type of vector that you would encounter or create in the 2D space. Therefore, we can say that these set of vectors do span R2. So yes, it does span R2. For the next example, we need to identify if a vector is part of a spanning set. So here, we similarly do the same steps like a while ago. First, we create the augmented matrix first. So in creating the augmented matrix, we use each vector as a column of the matrix. So we write 2, 1, 1, 1, -1, and 3. And on the right side of the augmented matrix, we write the vector that we are looking for. So 1, 5, -7. And we want to identify if it is part of the spanning set. Then, we take the RREF form of this augmented matrix. And by taking the RREF form of this matrix, what we are looking for are the constants or the scalars that satisfy the linear combination wherein we need to find the constants that when you multiply these to 211 and to another constant to 1 negative 1 3, it should get you to 1 5 negative 7. And if there is no solution, that only means that it is not part of the spanning set. So let's evaluate the REF form of this matrix. When you evaluate this, it should get you to this answer. And as you can see, that we have this matrix over here. You can also interpret this result as like saying 1, 0, 0, 0, negative 1, 0 times your scalars a and b, which should be equal to 2, negative 3. And by evaluating this, it should get you to a equals 2 and b equals negative 3. But because we have a solution, then we can say that this one is also part of the spanning set with these two vectors. To be able to verify this, you simply plug in the scalars and multiply that to the vectors and add them together to get you to this answer, 1, 5, negative 7, where a equals 2 is multiplied to 2, negative 2, 1, 1, and for b equals negative 3, you multiply that to the second vector. So next, we try to identify if the spanning set of the null space. So here we have our coefficient matrix A. So that is our coefficient matrix A. And this is our zero vector and the variable vector. So what we want to find out is the spanning set of the null space. So here, we can have two possible results in the spanning set of the null space. First, you have only the zero vector. Meaning, if you only have the zero vector as the spanning set, therefore that this one means that it is you have the trivial solution. And if it's a non-trivial solution, then that means that you have some vector wherein you have to multiply. When you multiply it with a constant, it will get you to the answer wherein this vector is not the zero vector. So let's find out whether this equation is really a zero vector, if this one has a spanning set of a trivial vector space or not, or basically if it has a zero vector or not. So how do we then interpret this? First, we don't need to create any augmented matrix. We simply go straight to taking the RREF of this matrix. And from there, we will find out the results. We basically observe the results and investigate whether it has the zero vector or maybe it's a vector that needs to be multiplied by something else. So when you take the REF of this matrix, it should get you to something like this. And when you multiply, when you basically think of multiplying it with a constant vector, then it should get you to this equation, wherein this one is equal actually to the zero vector, since it is again a null space, so it's a homogeneous system. So when you apply the equations by matrix multiplication, it gets you to a plus c equals 0, b plus c equals 0, d equals 0. So we have these three equations. But notice that we have C and we don't have any C over here, like C equals something. But that would mean that C is actually part of the real numbers. And the reason being so is that we need to show this since A and B are dependent on whatever the value of C is. So when we create the spanning set, our spanning set would look something like -1, -1, 1, and 0, multiplied by C, where C, again, is any real number. So where did we get -1 and 1? So here, we know from the solution, when we isolate A, B, and D, A is equal to -C, B is equal to -C, D is equal to 0, as mentioned a while ago, and C, since it has to be 1 because it's any real number, and so we'll just leave it as 1. So that would show us the constants that we got from this vector. And because of this will then become our spanning set. So our spanning set will then be equal to -1, -1, 1, and 0. And remember, in a spanning set, we are trying to make use of these vectors and create a linear combination. So when we're trying to get for the answers, or of the solutions rather, which are here, then we are multiplying this vector in particular with any constant, such that when we apply this with a constant and multiply it to this vector coefficient matrix, it should get you to the 0 vector. So this again would be the final answer for the spanning set of the null space. Next, we have then the concept of linear independence and dependence. So here in linear independence, we are taking a linear combination of vectors and it should get you to the 0 vector, provided that all your constants must be equal to 0. However, for linear dependence, it is basically a group of vectors in a vector space that are not linearly independent. And how do we then find out if it's linearly dependent? Simply negate this expression, all constants a sub I is equal to 0, to there exists a constant a sub I that is non-zero, which would then mean that a group of vectors are linearly dependent. So let's have some theorems regarding linear independence. If we are given a set of vectors in Rn, and A is the matrix whose columns or rows are the elements of S, then S is linearly independent if and only if the determinant is non-zero. So, how do we then create the relationship with these statements? So we know that we've been creating augmented matrices with each vector being the column vector. And on the right-hand side, we will have the augmented matrix having the 0 vector. Because we're trying to find out if the solution would give us only 0 vectors, or if there is a solution, then the solution would just be basically have all constants be equal to 0. But if not, then it would be, well, at least one would be non-zero, or there is no solution. So when we're trying to get for the value of this one, eventually you should get to the identity matrix. And again, in an identity matrix, only the diagonals would be equal to 1 and the rest of the values would be equal to 0. And we know that when we transform a matrix to the identity matrix, that means it is row equivalent. Meaning, you have a set of elementary row operations that would get you to the identity matrix. And based on what you've learned from determinants and matrices, you know that if it is row equivalent, then it's also it's equal counterpart, it's like saying also that A can be non-singular, or more importantly, the determinant would then be equal to a non-zero value. So, using this relationship based on the summary of facts that you have learned from determinants and matrices, this would then mean that first it's non-zero, the determinant, and S is linearly independent because the solution for each would be equal to 0. So there is a solution and all of them are equal to 0. So therefore, this theorem would hold. Another theorem would be that given a finite subset of a vector space, so let's name this S1 and S2, wherein S1 is a subset of S2. Then the following would then hold. If S1 is linearly dependent, then so is S2. So how do we show that? We're taking the linear combination of these vectors in S1, and we want to show that this is equal to 0. So, assuming that it is equal to 0, when you add them all these together or form a linear combination, it equals to the 0 vector, then that would mean that there exists a constant that is non-zero in S1. And so if we add them to the vectors inside S2 but outside S1, so basically the vectors around here, and add them to S1 vectors, then it would be linearly dependent because you still have some vector here that has a non-zero constant. So when you add them all together, it becomes linearly dependent. Whereas if it is linearly independent for S2, if S2 is linearly independent, then so is S1. So when all of these result to the 0 vector, then that means all of these constants or all of the vectors have constants that are equal to 0 when you try to create the 0 vector. And when you only include vectors in S1, all of them would still equal to 0 because S2 is linearly independent to begin with. So the smaller set would also be linearly independent. Another theorem is the non-zero vectors in a vector space are linearly dependent if and only if one vector is a linear combination of its preceding vectors. So when we try to create the linear combination for this one, we have A1, V1, A2, V2, A sub j minus 1, V sub j minus 1, A sub j, V sub j, A sub j plus 1, Vj plus 1, until A sub n, V sub n. So what this theorem is saying that if this vector is a linear combination of the other vectors, then that would mean that it is linearly dependent. So how do we show then that this is linearly dependent rather? Since this thing in green is actually a linear combination that would get you to AJ, VJ, we can substitute it like so. Assuming that the constants can be equal to 0, but we can see that we also have another AJ, VJ here. And if you want to get to the 0 vector, assuming that the other constants are also equal to 0, we can subtract this with the other vectors preceding it, which would cancel out. So this one would already be the 0 vector when you add these two together. And it would be linearly dependent since, number one, there are two vectors that are present which are inverse of one another. So one constant would already be negative and one is positive. So therefore, when we cancel them out, that gives us the 0 vector, which if we add the 0 vector to the other remaining vectors, then that would also be linearly dependent because when you multiply it with any constant, it would still be linearly dependent since multiplying any constant by 0 vector is equal to the 0 vector. So This would then show what the theorem describes. So now let's proceed with the exercises. So first, let's try to identify if this set is linearly independent. So we have a set of vectors in R3, and we want to show whether they are linearly dependent or not. So first, we create the augmented matrix. So like in spanning sets, we also create the augmented matrix over here, and basically add the zero vector at the right hand side because we're trying to find if it's linearly dependent or not. So after getting the augmented matrix, we then take the RREF of this matrix. And once you get the RREF matrix, the RREF of this matrix, you should get something like this. And notice that when our solution actually has all the constants b equal to 0, assuming that we are multiplying this identity matrix with the variable matrix a, b, and c, which all dictate the scalars that you are multiplying to each vector. So with that, that means that since all of the scalars are equal to 0, therefore it is linearly independent. For the next item, we have the set of vectors in R3, and we want to find the vector that makes it linearly dependent. So we know that this one is already linearly dependent, and we have to find out which specific vector is a linear combination of the previous vector, of other vectors as well. So first, we create again the augmented matrix, forming 1, 1, 0, 0, 2, 3, 1, 2, 3, 3, 6, 6. And then take the RREF of this matrix. And once we take the RREF of the augmented matrix, we get this answer. And by multiplying this with let's see, we're multiplying it with the scalar vector a, b, c, d, because there are 4 vectors. This gives us the result of the following equation. So this is a plus 2d equals 0, b plus d equals 0, and c plus d is equal to 0. And notice again, like in the previous items, that a, b, and c are dependent on whatever the value of d is. So in this case, d then would be any real number. So with that, the solution would look something like a vector again. So in this vector, we have first, let's isolate the constants. A is equal to negative 2d, b is equal to negative d, c is equal to negative d, and d is just a real number. So with that in mind, we can multiply d to a vector negative 2, negative 1, negative 1, and 1. And with this, we actually have a solution or spanning set that constitutes what the solution set for this vector is. When we want it to reach, or when you make a linear combination, it results to the zero vector. So the fact that it is not the zero vector as the solution means that it is in fact linearly dependent. So let's try to find a value for d that would show that some vector is making it linearly dependent. So d, let's say d is equal to 1. Then the other vectors would other constants or scalars would follow, wherein a is equal to negative 2, b is equal to negative 1, and c is equal to negative 1. When we apply this to the vectors on the right hand, on the given, we have negative 2 multiplied by 1, 1, 0 minus 0, 2, 3 minus 1, 2, 3 plus, because d is equal to 1, 3, 6, 6. And if you look at the linear combination, you could see that this entire vector produces the result -3, -3, -6, and -6. Wherein this other vector is 3, 6, 6. So notice that these other vectors have to form some vector that when you add it to this 3, 6, 6 vector gives you the 0 vector, which makes use of the theorem that was mentioned earlier, wherein the one vector is a linear combination of the previous vectors. So with that in mind, that would mean that this vector is making it linearly dependent, because you have three vectors that create the similar to this other vector wherein you're multiplying it by -1, and or its inverse, additive inverse, that when you add them it gives you the 0 vector. So that means that the vector that makes it linearly dependent is actually vector 3, 6, 6. And when we eliminate 3, 6, 6, you can verify for yourself that by removing this vector in particular, the result would be linearly independent. When we remove this vector, you create a set that is linearly independent. So next, we have vectors in the null space, and you want to determine if they are linearly independent. So again, like in the previous items, first, create the augmented matrix, giving us 1, 2, 0, 1, 1, 0, -1, 1, and 1, 6, 2, 0. And then, once we have this, before we proceed, we actually forgot one more step, adding the 0 vector. Once we have the augmented matrix, we again take the RREF of this matrix and observe the results that we will get from this one. And when we get the RREF of this matrix, we get something like this. And as you can see, there is a consistent solution, and that solution is actually wherein the constants A is equal to 0, B is equal to 0, C is equal to 0, assuming that we're multiplying this matrix on the left-hand side of the augmented matrix with the constant matrix A, B, and C. And since all of them are 0, that means it is, in fact, linearly independent. For the next item, we want to identify the vectors in a set that is part of a spanning set. So in this item, we're looking for a smaller set that, since if we're making it smaller, that means that there's probably a vector that's making this entire set linearly dependent. So let's create first the augmented matrix. So here, we basically combine again all vectors. And in the right-hand side, we have the 0 vector. And then second, we take the RREF of this matrix and see where this one will, what will this show us regarding the linear independence or dependence of the set of vectors. And when we do that, you should get something like this, wherein, as you can see, we can form again systems of linear equations with regards to the scalars that we will multiply to the matrix. So based on the equations, let's add it here for formality. So multiplying A B, C, and then D. So we have A plus D is equal to 0. B plus D is equal to 0. C is equal to 0. And again, as you can see, two scalars are dependent on the scalar D. So D would then be any real number. And with that would show us the solution that when we multiply D to a vector, that gives us -1 since A is equal to -D. And similar to A is also B, wherein B is equal to -D, so -1 will be multiplied here. C is equal to 0, and D is any real number, so 1. And then that would mean that your solution would be -1, -1, 0, and 1. But that's not actually what we're looking for. We're looking for the spanning set S of 1, wherein we have the set that spans some set W. So here, we have to observe then that we have to remove some vector in particular in the given set to make it linearly independent. So as you can see, vector number 4 is what's making it linearly dependent. And in addition to that, you can see that these two vectors are actually, when you add them together, gives you the fourth vector. So with that, we can eliminate vector number 4, and this one would then give you the spanning set. So S of 1 would then be equal to the other three vectors. So 1, 1, 0, 0, 1, 0, 1, 0, and 0, 1, 1, 0. And this would then be your vectors that will become part of another spanning set, which also span the same set W. So that is all for linear independence and spanning set. So one thing to remember always is to first create the augmented matrix, if necessary, because you may have a given item where you're given the coefficient matrix and you're tasked to find the spanning set of the null space, which we have done earlier, and that does not require the augmented matrix. And you should also remember, in an augmented matrix, you should remember which exactly should be on the right-hand side, whether it's the 0 vector or maybe you're representing any vector. So you can represent it as X and Y, like in the examples from the spanning set. Second of all, you take the RREF of the matrix. And once you get the RREF of the matrix, you observe the solution. Observing the solution would give you insights whether it's linearly independent, linearly dependent, or whether you have some solution that would give you the spanning set of the null space, or it can give you a solution that that would show us that a set of vectors are part of or span some sort of vector space. So these three steps are important in being able to answer items that are related to linear independence and spanning sets. So that is all for this video. In the next video, we will have topics regarding basis, dimension, and the rank of a matrix. Additionally, we will sum up everything together to make sense of the concepts that we have discussed since vector spaces and subspaces.